Alright, welcome back to the channel. I just watched Pissy Warrior's latest video on Coriolis Force, and I have to say, what a masterpiece. And by masterpiece, I mean an absolute piece of shit. I don't think Leaky got anything right in that video, so I'm here to correct him and steer you in the right direction with Coriolis. The first mistake that Leaky makes is claiming that the atmosphere and the ground are two separate reference frames. This is absolutely and demonstrably false. When you jump off the ground at the equator, do you start moving to the west at 1,000 miles per hour? No, I don't think so. When you jump off at the ground at the equator, you're taking your rotational velocity, which is 1,000 miles per hour eastwards, with you, and you rotate with the ground. This is equivalent to you jumping up and down in a train. You don't fly to the back of a train when you jump up, rather you land the same spot that you took off on. Now, if you jump off a train, onto the ground, that will be a separate reference frame. And as you go ass over tea kettle, next to the train tracks, it'll become quite obvious that it's a separate reference frame. Coriolis Force, even though being in the atmosphere, you're still in the same reference frame as the ground, Coriolis Force is apparent as we travel northwards or southwards. Let's start off at the equator. We take off, we have 1,000 mile per hour rotational velocity to the east. We take off, and initially we just rotate with the ground. What happens as we travel northbound? All of a sudden the ground underneath us no longer has 1,000 mile per hour eastwards rotational velocity. The further north we go, the less the rotational velocity is to the east. So as we fly northwards, we're going to start curving to the right. Because keep in mind, we're still keeping our 1,000 mile per hour rotational velocity. So the further north we go, the more to the right we curve as we keep our 1,000 mile per hour rotational velocity. Now let's take a look at flying southbound. Let's start off at the North Pole. We have no rotational velocity at all. We'll take off. And the further south we go, the ground starts rotating underneath us. The ground has a rotational velocity to the east, we do not, so once again we start curving to the right. Flying in curved lines, whether it be from the south from the North Pole or north from the equator, is not efficient. But luckily we're in an airplane, we have navigational computers, we have control surfaces, and it's very easy to course correct. We take off from the equator and we're headed to Italy here. As the airplane starts being affected by Coriolis, as it starts curving to the right, all we do is we correct our heading and we keep our airplane headed towards Italy. There's no need to take off in this direction and let the Coriolis curve you to Italy. You just take off in a straight line, great circle route towards Italy, and you just course correct as you're flying. Now, if the airplane did not have control surfaces or a guidance computer, then you would have to aim off the west of Italy, launch this way, and let Coriolis bring you to Italy. This will be something like artillery shells. You would have to correct for Coriolis, because once you're in there, there's no correcting. So you have to make all the corrections before you launch or before you get fired out of a cannon. Let's take a look at the southern hemisphere. We will take off from the equator, we fly southbound towards Antarctica, and we take off, we have 1,000 mile per hour rotational velocity this way, and as we fly, we get over areas of ground with less rotational velocity, so we're going to start curving to the left, because we're bringing that rotation velocity, initial rotation velocity with us, and we start curving to the left. If we start off in Antarctica, and we fly northbound, we have no rotational velocity, and as we fly northbound, the ground will start rotating underneath us, and once again we start curving to the left. So in the northern hemisphere, we curve to the right. Southern hemisphere, we curve to the left. All right, so now that we know that objects in the northern hemisphere curve to the right and southern hemisphere curve to the left due to Coriolis force, Let's take a look at low pressure systems, extreme low pressure systems, hurricanes, typhoons, cyclones, that kind of thing, in the northern hemisphere and in the southern hemisphere, and we'll see which way we curve. So in the northern hemisphere, we have a low here, and everywhere around the low, we have high pressure. That's a definition of low pressure here, high pressure all around. So everywhere, the air pressure is going to try to move from high to low. Move in like this. Here, going to try to move high to low, high to low. Now what happens, remember, due to Coriolis force, any objects traveling north or south with a north-south component to them, they'll take a turn to the right. So high to low, and it takes a turn to the right. High to low takes a turn to the right. High to low takes a turn to the right. High to low takes a turn to the right. And we set up a counterclockwise rotation. So in the northern hemisphere, the low pressure systems, they spin counterclockwise because of Coriolis force. The opposite is true if you're south of the equator. So let's go south of the equator here. In the southern hemisphere, we have a low pressure system, high pressure all around. And there's going to want to move high to low, just like this. But remember, we're in the southern hemisphere, so due to Coriolis, stuff takes a left-hand turn. So takes a left turn, left turn, left turn, left turn. And what we're doing is we're setting up a clockwise rotation. So extreme low pressure systems in the southern hemisphere, they rotate clockwise. There you go, that's due to Coriolis.